Welcome back, and in this video I want to talk a bit more about this technique of iteration for solving these nonlinear equations that we end up with when we try and do circuit analysis for diodes. The basic idea of iteration is that we take a guess about what either the voltage across the diode or the current through the diode is going to be in our circuit, and then we work out, given that assumption, what the current or the voltage across the diode would be, whichever one we haven't guessed. We then compare that calculation with what the Shockley equation would predict. Given the results of that comparison, we can then make a better guess about the voltage across or the current through the diode. Repeating this process over and over again gets us to a very good approximation of the actual voltage and current of that diode. I'm sure this will be much clearer with an example, so let's work through the same problem that we saw in the last video. The problem is that we have a 10 volt voltage source, so this point in the circuit is at 10 volts. And I have a forward biased diode there, which has a saturation current of 1 nanoamp and an ideality factor of 2. That then goes into a 1K resistor, and the other side of that 1K resistor is just connected to ground. Right. I'm going to start off by guessing the voltage across this diode. Usually I will guess the voltage and then work out the current. And in this case, I'm going to start with a first guess that the voltage across this diode is 0. Now that's not a particularly good guess. In general, it would be better to guess a voltage across a forward biased diode like this to be around about 600 millivolts or so. The closer your original guess is to the right answer, the fewer iteration steps you have to do. But in this case, just to show the method, I will take an intentionally not very good guess and start off assuming that the voltage across this diode is 0. Right, if the voltage across this diode is 0, then the voltage at this point in the circuit here, I've called it V resistor in the table on the slide, that's V resistor there, is 10 volts. If this is 10 volts, then I can work out the current through the diode, because I can see in the circuit that the current through the diode must be the same as the current through the resistor. So the current in the circuit is just 1 or 10 volts divided by 1K or 10 milliamps. And that's my first guess of the current through the diode. So I have guessed that the voltage across the diode is 0 volts, and that has led me to the conclusion that the current through the diode is 10 milliamps. Now, we compare that result to what the Shockley equation would predict for my guess, the voltage across the diode. I can rewrite the Shockley equation in the form the voltage across the diode is 25 millivolts times the ideality factor, and 25 millivolts times, in this case, 2 would give me 50 millivolts, times the natural logarithm of the current through the diode divided by the saturation current plus 1. And this formula just comes from taking the Shockley equation, I equals Is e to the power of V over N 25 millivolts minus 1, and doing a bit of algebra on it. This equation here then predicts that the voltage across the diode, if the current really was 10 milliamps in the circuit, would be 50 millivolts times the natural logarithm of 10 milliamps divided by the saturation current, 1 nanoamp, plus 1. And working that lot out gives me 50 millivolts times the natural logarithm of 10 millivolts divided by 1 nanoamp plus 1, or 0.8059. So that is predicting that the voltage across the diode would be 0.8059 volts, which is clearly not 0 volts. If 0 volts was correct, then my guess and the prediction of the Shockley equation based on my guess would be equal. They're not. So I need to make a better guess. And the second guess that I use is this one, what the Shockley equation predicts the voltage to be. I've just put it to 3 significant figures on the slide, 8.06. So we can now do a second iteration. Let's guess that the voltage across the diode is 0.8059 volts. Then I can work out the current flowing through. Well, if the voltage across the diode is 0.8059 volts, then the voltage across the resistor must be 10 minus that, or 9.194 volts. If the voltage across the resistor is 9.194, then I can calculate the current through the resistor just by Ohm's law, 9.194 milliamps, and that must be the current flowing through the diode as well. So let's test this second guess, this 0.806 volt guess. What would the Shockley equation predict the voltage across the diode would be if the current was 9.194 milliamps? It's like checking how accurate our guess is. Put that value into the Shockley equation here. The answer is 0.8017. So, my second guess looks like it isn't that far off. I've guessed 0.806, worked out the current, and used the current to predict what the voltage across the diode would be. If my guess was right, they would be equal. They're not quite equal, but they're not far off. So I'll need to take a third guess. And again, the third guess that I will pick is this one, the result of the Shockley equation using the current from my second guess. And that leads me to this. Guessing that the voltage across the diode is 0.8017 results in a voltage across the resistor of 9.198, and therefore a current through the resistor of 9.198 milliamps. And that current must be the current flowing through the diode as well. So let's put that into the Shockley equation and see what the Shockley equation would predict for the voltage across the diode with that current flowing through it. Answer 0.8017, which is exactly the same as it was. I've now got a consistent guess. The current being predicted by Ohm's law across this resistor, and the current being predicted by the Shockley equation through this diode are now the same. So I've got a solution, a consistent solution. I can just fill this in on the fourth row of my table here. That is my fourth guess. This is the voltage across the resistor it would predict. This is the current. The predicted current has now not changed. It's another way of knowing that you have reached the end. You've done enough iterations. When the value that you're getting out of your iterations doesn't change within the accuracy that you're working to. In this case, 4 significant figures. So I'm now quite happy that I've solved my circuit, and the current flowing through this diode would be 9.198 milliamps. And the simulator agrees, which is not surprising, since this sort of calculation is exactly what the simulator is doing to try and work out the current through this circuit. So, just to summarise the method. First step, guess the voltage across the diode. Within reason, it doesn't really matter what your guess is, but the more accurate your initial guess can be, the fewer iteration steps you'll have to do. So a good guess for a forward biased diode would be around about 600 millivolts if the diode is forward biased. Secondly, solve the circuit assuming that your guess is correct. You could think about that as replacing the diode in the circuit with a voltage source of value VD, and then solving the resultant linear circuit. Once you've got the linear circuit, note the current flowing through the diode. 4. Use the current that you've determined flowing through your diode to determine the voltage across the diode using Shockley's equation. To determine VD based on this current. If the VD hasn't changed since your last go through this iteration procedure, or has changed by an amount within the accuracy to which you're working, stop. Otherwise, use new VD from Shockley's equation. That's the one you determined in step 4 as new guess. And go back to stage 2. And keep going round that until your value for the voltage across the diode, or for the current flowing through the diode, whichever one you're trying to solve for, hasn't changed to within the accuracy to which you're working. Okay, next time, a quick look at the static and dynamic resistance of diodes.